Good morning. My name is Jean-François Guérin. I am the project director, the HyPSTER project director for Storage.
And I am Grégoire Evin. I'm a salt cavern expert, and I the coordinator, scientific coordinator of this project.
Okay, so Grégoire and I are going to present you the results, the main results that we have achieved on this work package 3. Work package 3 being the demonstration of hydrogen storage and cycling in a salt cavern. So this work package actually has two main objectives, and Charlotte has mentioned them. The first one is to produce green hydrogen, hydrogen produced from renewable energy. So in that, to meet that objective, we had to design, construct, and start up a green hydrogen production facility. This facility had to include a 1 megawatt PEM electrolyzer, proton exchange membrane technology electrolyzer. And also it had to be fitted with a tube trailer filling station. So that's one side of the project. The other side of the project is the demonstration, the feasibility of storing and cycling hydrogen in a salt cavern. And the main steps that were identified to meet that objective was first to design, select, and install subsurface equipment in the so-called EZ53 platform on the HyPSTER site. That's the name of the well, number of the well. And Charlotte mentioned that we had to design specific equipment for that demonstrator. Second, we had to test, we identified that we had to test the tightness of the storage cavern for both nitrogen and then hydrogen. And finally, to demonstrate the feasibility of storing hydrogen and cycling, we developed a program to carry out cycling tests of hydrogen stored in the cavern. And the intent is to study the behavior of the system composed by hydrogen and rock salt under the effect of the pressure variations that we will apply. So Charlotte mentioned that this demonstrator is located in Étré-Bresse-Vallon. On the left-hand side, you can see roughly where the site is located in France. It's about 90 kilometers north of Lyon. On the right-hand side, you have an aerial view of the Étré site. Étré site is a major storage site of natural gas, underground storage site for natural gas. The gas being stored in salt caverns. So the gas main central station is surrounded by the blue line on this picture. The EZ53 platform is located about 300 meters south to the plant. So this is where the storage demonstrator is located. And then, on the left-hand side, about 200 meters away from the storage platform, you have the hydrogen production platform, which has been constructed. So the main results that we have achieved and that we are proud of regarding the green hydrogen production, the facility has been built. A small quantity of hydrogen has actually been produced early October during the startup phase. After that, we ran into some problems with the electrolyzer. I will get back to that. But still, we have produced some hydrogen. Regarding the storage demonstrator, we have achieved very important milestones. The workover of the well was carried out in March 2023. The nitrogen tightness test was successfully performed in 2023 over the months of October and November. And one of the very important milestone, Charlotte mentioned that, was the first hydrogen injection that we had been waiting for some time. So that took place on October 3rd, 2024. That allowed us to start the hydrogen tightness test of the well. And finally, the major, biggest milestone of the project achieved so far, we have demonstrated the tightness of the well and the cavern to hydrogen. That was completed in November 4th. No leaks were detected either to the control annular or to the debrining completion. So this was really a major success for the project and a major milestone that was reached at that time. The main challenges, we had difficulties with the supplier of the electrolyzer. Proton exchange membrane is still an emerging technology. At the time where we are developing the project through the design phase and the construction phase, at the same time, the supplier, Elogen, was still in the development stage of his electrolyzer. They had to find ways of producing the stacks in a reliable manner. So this led to some delay in the commissioning of the production platform. And also we had some troubles with the transformers. I will get back to that later on. On the storage side, we had safety is the utmost priority to Sorenji, and especially safety in operations. So we put a lot of time and emphasis on designing surface equipment which can be operated safely at a very high pressure and with nitrogen. 350 bar G is the pressure that we have when we connect the discharge line to a truck trailer. At Sorenji, we are not used to that kind of very, very high pressure. And also, we were not used to dealing with the hydrogen molecule. Vous m'entendez? C'est bon? OK. Donc, attendez, je reprends. Ça passe plus. That's the bug of the day. Okay, thank you. No, it's before that. Okay, and okay, the last and third challenge that we faced was to design a safe procedure to directly measure the hydrogen brine interface level using PNT by logging in a hydrogen environment. This was really new to Storengy, so we spent a lot of time on this procedure to make sure that there would be no problem the D-Day when we would run this logging. And also, this was really a first for the Storengy teams, this kind of logging, because actually they are used with to do this in a natural gas environment. And Grégoire will talk about it later on. Okay, thank you. Okay, now moving to the results for the H2 production side. Here I just show a schematic of the process. This is very classical process for hydrogen production and distribution. So as I mentioned, the electrolyzer is a 1 megawatt PEM electrolyzer. It has 4 stacks, and the producing of the stacks was a bit complicated with Elogen. It took them a lot of time to find ways to produce them in a reliable manner. The electrolyzer produces hydrogen at 30 bar G, and this hydrogen is fed to a buffer tank located at the suction side of the compressor. And on the discharge side of the compressor, you have 2 dispenser panels which allow to fill tube trailers. And also the produced hydrogen is purified to mobility grade quality requirements within the electrolyzer package. Just to show you a few pictures of the actual facility that was built. So on the left-hand side, you can see the electrolyzer and the associated thermal skid. And on the left-hand side, you can see the compressor that was supplied by Hoden and the hydrogen buffer tank. And here are the 2 tube trailer filling stations on this site. So as I mentioned, during the startup of the electrolyzer, the supplier encounters some problems with the transformers. These have to be replaced, so it's a major impact on the schedule of the project. The lead time is about 4 months. So this leads us to have rescheduled the startup of the electrolyzer in June 2025. And also the commercial operation date of the production platform is now scheduled for the summer of 2025. And now I leave the floor to Grégoire.
Thank you, Jean-François. I'm very happy to share with you the first result of this project. I have worked a long time for that. So it's really something very important for me. Just to show you the principle of the element in surface around the cavern. Here we have developed things to be able to inject hydrogen in the well and to move things with brine and brine storage and water also for dilutions. First work was to First thing was to develop a special completion inside the well. It was in 2023, we set the new completion with everything more specific for hydrogen. You can see the wellhead from Technip FMC equipment inside the completion by Schlumberger and the tubular by Vallourec. All these equipment were tested for hydrogen. And maybe the specificity of this completion is to have 2 safety valves, one safety valve on the central tubing and another safety valve on the annulus, to be able to close the well if necessary on hydrogen or on brine. Some photos of the project. So you can see the brine tank and the wellhead. And on the wellhead, you can see the panel to connect a tube trailer to inject hydrogen. This is inside of the brine skid with a pump of brine and pump of water for dilution. So the first result is a tightness test. We started to test the cavern with nitrogen because nitrogen is not the same hazard because nitrogen is easy to provide. And then we decided for test the well and the cavern to have a sort of extensive test with 3 steps, a step inside the well and step under the casing shoe, and last steps where the interface is at the top of the cavern. And in fact, it was to test the completion first, the connection with the rock salt, so the cemented casing and the casing shoe, and then to have an opportunity to develop, to add a third interface to check the behavior of the gas in contact with the salt. This test, we did this test in end of 2023, 1 year ago, and we have no special difficulties with this nitrogen test. Just to give you an element on the second interface, we inject the hydrogen, so you can see the pressure increasing a little, and so we have a period, we wait a period of stabilization, and then we start a period of observation of the interface. And the idea, and it is the principle of such a test, is to check if the interface is moving, changing, especially going up. If it's going up, it's probably a sign of pore tightness because we lose a part of the gas in the upper part. And to check the position of the interface, we use a special tool inside the well, so going down to measure directly the interface by a system of pulse neutron to be able to have a clear sign of the position of this interface. And you can see on the right that the first measurement, we find the interface under the casing shoe about 864 meters. And we wait 2 days, and after 2 days, we have a second measurement. And the second measurement, you can see that the interface moves slightly down, 25 centimeters down. So it's a good sign of the tightness of the system. And it's the fact that the interface goes slightly down is more linked to the stabilization of the pressure in the cavern. You know, or you may know that in a cavern you have a lot of phenomena, creep, thermal equilibrium, chemical equilibrium with the saturation of the brine inside and so on. And so it's always this sort of parasite phenomena who can lead to misinterpretation of test. But in this case, we wait probably, we have not probably a perfect stabilization. So that's the reason why we have this interface going slightly down. But it's very, very thin. So we were very happy with this first result because the completion was very tight to the nitrogen first. And then we repeat the operation. And I try to repeat the operation, yes. We repeat the operation with hydrogen this time. And so first interface, second interface, third interface, exactly the same test. The idea is to have a good basis for comparison also of the behavior of the cavern, because as I said, we have parasite phenomena. And so to avoid misinterpretation, we want to check if the behavior with hydrogen is the same that with nitrogen, or if we can detect the specificity in the behavior of hydrogen. This test was done in October, as Jean-François said, and we get a very good result. And I just focus on the second one also to have the comparison. Finally, very similar to the nitrogen behavior. We have the injection, waiting time, and the period of observation with 2 measurements with a log. And you can see that the pressure is more stable. So probably the equilibrium in the cavern is a little better than for nitrogen. And finally, we reach a very similar result with this time only 13 centimeter of difference. So something very, very thin. If I apply a classical criterion of validity of such a test, it's possible to calculate a minimum detectable leak rate. This minimum detectable leak rate, in this case, we have an uncertainty of 10 centimeter in the measurement. So it represents a volume in my cavern neck in the area of the interface of about 5 liters. And so in this case, with this difference of 13 centimeter, it represents more or less 6.6 liters for 2 days, and we calculate for 1 day, so an half, so 3.3 liters. So is largely under the maximum allowable leak rate. So it's a very simple way to interpret the result, but we are very confident in the fact that there is no problem of tightness in this cavern. And so it was a very good result, and it opened the possibility to develop the project by injecting more hydrogen. So this is the achievement of the test. And for the next step now, we are working on the first hydrogen injection. So injection of about 2.5 tons now, because we have already hydrogen. It is in progress. Today, you can see on the picture that the yellow line is the current interface. So we fill the upper part of the cavern, and the light blue line is the target. We will finish this filling. Oh, it's a small filling, but it is a filling. We will finish the filling next week. We are waiting for the last tube trailer with hydrogen. And the cycling test will be start the week after, probably. And so it will be developed until March 2025. And we will also take samples of hydrogen before and after, and to check the exact composition of hydrogen we inject, and the result after 3 months in the cavern. Yeah, just short picture. You can see a tube trailer and the connection to the wellhead, and very quickly the cycling we imagine. So the principle is to fill the upper part of the cavern with hydrogen and withdraw the brine at the same time. And then after that, we will close the well on hydrogen's side and just inject brine to pressurize and withdraw brine to depressurize the hydrogen and simulate like this cycle of pressure of hydrogen in the cavern. 100 cycles are planned, and we will finish. You can see the cycle on the right with small cycle and large superposition of short cycle and large cycle to test less good possibility of gas operation in this cavern. And we will finish by withdrawal of the hydrogen, a final withdrawal. It is the last part of the curve. And I thank you. I'm ready for eventual questions.
Thank you. Thank you. I'm Sylvie from Equinor. Just, I had a question about the timing of the project, because you are now filling the cavern with the trailers, right? But the electrolyzer will not be in operation until June, but as I understand, the cycling process will be by the end of March. So what is the plan when the electrolyzer comes into operation? And also I had some questions about the electrolyzer itself, but I can...
The initial intent was in effect to have the electrolyzer producing hydrogen to be transported with tube trailer to fill the storage demonstrator. That was the initial intent, but then the two schedules were not in line, and there was a risk at what point in the project that there was a risk that the electrolyzer would not be in service when we had to inject hydrogen. So that's why we decided at that time to place an order with Life to actually buy the hydrogen from a producer and to store it, just to de-risk the schedule of the demonstrator, or the storage demonstrator. And in the future, when we put in operation the production facility, that would be next summer, then the intent is to commercialize the production to local distributors so that they can use the hydrogen for mobility purposes.
Okay, thank you. So the production from the electrolyzer itself will not go into the cavern per se? No. Okay, I understand. So the electrolyzer is grid connected, yes?
For electricity?
Yeah.
Yes.
Yeah, okay.
Yeah.
So is that a commercial type of electrolyzer you have from Elogen?
Yeah.
It's you have some experience from before with the performance data and things like that? Is it an off-the-shelf kind of electrolyzer, or is it also a part of an R&D or a technology development project?
As I mentioned, that they were going through developing the electrolyzer when we procured it. And now I think they have learned a lot from this project as well. And now I think they have moved to a bigger size electrolyzer. I think they moved to 3 megawatt. So, but this was part of their development, producing this type of electrolyzer.
Okay. Yeah. Okay, thank you.
Thank you. We'll just take a question online, and then I'll go back to you.
So we have a question through the chat from Augustine Bogumil, who is saying, Jen's nice presentation, kindly ask about leakage from PQE during H2 MIT test pulse logging.
Maybe I can show the picture. Yeah, the principle of this test is to check if there is a leak in the well and in the upper part of the interface. So, if something leak, hydrogen go somewhere outside of the well and outside of the cavern, and so we have a miss of hydrogen quantity in the well, and we well know all the volume and the quantity of hydrogen we set, so the interface go up. And so it is very important to have a good measurement of the position of this interface. And so you can see here that during the test, the pressure slightly decreased, but it's very, very small. We are looking for very, very small quantity. And that's the reason why probably there is not a perfect stability of the cavern in the brine, probably linked to the level of saturation of the brine inside the cavern. So if the cavern is not, if the brine is not saturation, there is new dissolution. So it's decreased a little the volume of brine inside, and that reason why the interface go slightly down. But we are looking for something very, very thin, and that it is at the limit of the uncertainty we are able to check. And that's what the reason we have, for example, this way of interpretation with minimum detectable leak rate and the maximum allowable leak rate, which is 3 times the minimum detectable leak rate. And in this case, we are largely something under the maximum allowable leak rate. I hope it's under. It's reply to the question. It's okay.
Okay, the next one.
Yes, Romain Bocquet from Geostock. Just a question on the test with hydrogen. You said all the equipment was tested to hydrogen. Yeah. In all your tests for tightness test, for example, at some point have you tested the annular safety valve to hydrogen by closing it?
Yeah,
performing an inflow test.
We did it with nitrogen, and we have a short time to did it with hydrogen. So the safety valve is operated from surface by the control lines. As you can see, maybe here. Oh, sorry. Yeah. So it is these 2 valves. And especially the annulus safety valve is this one. The level of tightness is coherent with what we get, but we have a slight leak, very small leak in this tightness, but it is very well operating. No difference. We didn't see difference between the nitrogen and hydrogen at that time, but we have not a lot of extensive time to test this equipment. So we imagine to really test it when we did the final withdrawal of hydrogen, and just before to have hydrogen in pressure and to close the valve, withdraw hydrogen over the valve and wait a little to see if it's correct and to have more extensive control of this safety valve at the end of the experiment. After the first filling, we want to go very quickly to the tightness test. So we have no enough time at the time to check if we have exactly the same behavior between nitrogen and hydrogen.
Okay, thank you.
We have many questions. So we'll continue in the room.
Good morning, Ilaria Conti from the Florence School of Regulation. Thanks, this was a very interesting presentation. I have a technical question, and sorry if I missed it or if it's going to be discussed later, but regarding the timing of injection and extractions. So how long, you said you're injecting 2.5 tons of hydrogen. I was wondering what's the timeline? So how long does it take, and how long does it take then to extract the hydrogen compared to natural gas in particular? Second question, sorry, regarding safety. I was very happy to hear, I mean, all this attention to safety. I think it's essential. I was wondering if there's any specific protocol that you are following, or if there's like maybe a specific regulation in place in France for these safety measures. Thank you.
Okay, first question, the filling with hydrogen. Actually, it's going to take us total about 2.5 weeks. But it's really depending on the thing is the limiting factor, I would say, is the mobilization of tube trailers. Basically, when we have one tube trailer, it takes a day and a half to discharge the one tube trailer from 350 bars to 110 bars. This is we decrease the pressure inside the well by withdrawing brine to lower the pressure so that we can discharge the maximum amount of hydrogen from one tube trailer. So and roughly this is 1 day and 1 day and a half. Second question was with regard to safety. What we did prior to injecting hydrogen the first time before October, we ran a helium test, pressure test at 380 bar G, just to make sure that we would have no problems when injecting hydrogen. So this is one thing we don't do on other projects, but we decided to do this test just to make sure that we would not have any problems when we would be connected to a tube trailer at 350 bar G of hydrogen.
We are a natural gas operating company, so we have protocols and safety procedures and a lot of things. And we had to adapt this procedure to hydrogen because hydrogen is not the same gas with specificity. The density is different, the viscosity is different, and everything. So necessarily we have different things and safety procedure with, for example, the fact that a flame of hydrogen is not visible. So we have to add in our habitual procedure the use of thermal camera and so on. So yes, we work on that and we develop specific training also for people. For the question of the cycling, of course, this is an experiment, so we have limitation of this experiment. But if we want to project for the future, what we know it is that it's possible to go hydrogen a little. We have limits for natural gas about 15 meters per second in the pipes, and for hydrogen, due to this specific density and specific things, we probably could go 3 times this speed in the pipe. So it is adaptation, and we will probably could go very quickly for hydrogen and high cycling necessarily. It is not exactly our case in this experiment because it is experimental condition. Comme ça? Okay. Sorry about that. I will pay attention to the I promise. And so it is not necessarily representative, but we can, I think, transport the same quantity of energy because there's a high speed possible due to the specificity of hydrogen.
Yes, we received many questions online, but we won't be able to answer all of them. So we will send it to you, and you will send them an answer. So thank you so much.